je ferme rapidement.
Bon, j'ai lancé cela. Je ne sais pas pourquoi ça n'a pas encore connecté.
We are streaming now.
At least we should be streaming now. I wonder if it takes a few seconds to start or what.
Maybe wait for some people to join.
Okay, cool. Started properly. Awesome. I guess we can wait a few minutes for more people to join before we start. I think we can wait for maybe like 4 more minutes and then we start at 10 past.
Yeah, no problem. Can you hear me?
Yes, I can hear you perfectly. Awesome.
Yeah, no problem.
Cool. Since we are nearing 10 minutes past, I think we can start now. Hey guys, hi everyone who is joining. Hey Idris, awesome to have you guys here. So today we are having Willy Carlos Tchuitcheu that will be presenting his work to us. And so, cool. So it is my honor to be the host for this presentation and welcoming Willy here to present to all of us his very cool research. So Willy has received or had received his master's degree in mathematical sciences from the AIMS Institute. So AIMS stands for the African Institute for Mathematical Sciences. So he did that in Rwanda in 2019. And before kind of going there for his master's, he got his bachelor's degree and his master's in computer science from the University of Douala and Yaoundé 1 in Cameroon. So he did those in 2014 and 2015, respectively. Then he kind of did a couple of years as a research engineer at KmerAI. And so that is kind of like a research center in Cameroon for those that know it. And then after that, he kind of like spent some time as a guest research scientist at the Brandenburg University of Technology in Germany. So he did that in 2019. And now he's kind of pursuing his PhD degree in mathematics within the Department of Mathematics and Data Science at VUB. And so he's affiliated with the Digital Mathematics Research Group, and his research interests encompass a very wide field. So it includes like graphical representation learning, natural language processing. So for those of you who kind of like have heard about ChatGPT, so that's involved in natural language processing and machine learning in general. So he really has like a very wide area of research interest. And so it is really cool to have him here presenting to us. So without further ado, I'm going to pass it on to Willy to present to us. But actually before that, just to kind of like lay the way the presentation is going to go, we are going to have questions at the end of the presentation. And but feel free to put all of your questions in the chat throughout this presentation. And at the end of the presentation, I will kind of like go from the top and relay the questions to Willy. Cool. So without further ado, thanks Willy for coming by and thanks for presenting your work here.
Yeah, thank you, Zerot, and thank you for having me. So it's my pleasure to give a talk here at KmerAI. So today I'm going to talk about this. Our recent work has been published in pattern recognition, table representation learning using heterogeneous graph. And this work was conducted under the supervision of my two promoters here, Dr. Tan Lu and Professor Andoms. And our research group, so it's actually related to this artificial intelligence of our university, VUB. And yeah, I'm working as a PhD researcher, as you mentioned. So as outline of this talk, yeah, we'll discuss some key points of this paper. Basically, 5 points. And the first one is, I think it's important to start with the fundamental definition and concept. And within this section, so we'll need to first introduce heterogeneous graph. So just to be, we'll not go deeper into it, just to highlight what heterogeneous graph is. And then we are referring to this as a letter J. And secondly, we will talk about this human perceptual table understanding. So how, as a human, we do in terms of table understanding. So we will refer, whenever we are talking about table, we will refer this to as D. And of course, we need to cover a little bit about this representation learning techniques in NLP, natural language processing. And we can also discuss some key pattern in data modality. So here we are referring to text and table, because even though at certain point we feel like it's the same thing, but they have actually different pattern. And and in the second section we will talk about heterogeneous graph table modeling. And here we will actually highlight how we are mapping a table D into a graph. And secondly, what is semantic metapath? Semantic metapath is actually a technique to extract meaningful path from a graph. And how to extract meaningful path. So this is what we implemented a probabilistic random walk. And the third section, we will focus on our framework, graph-based table representation learning, where we'll emphasize on the architecture that we propose for this in this framework. And later on, we will also give an overview of the framework. And the fourth section is actually the experiment section, where we start by giving us a data set, not a data set, but just to cover what we did. First of all, we propose a new data set, and then we also run our method on public data sets. So we will present the result on these two data sets. So, and in the third section, we will conclude and give some perspective. So this is actually the highlight. So I will directly start by giving a fundamental definition and concept. So we have an heterogeneous graph here. What is the goal of the heterogeneous graph? In this figure, especially on the left side of the left part of the figure, so we have some graph, and it can be seen as a non-Euclidean data because we cannot compute the distance between two nodes without using the structure of the graph. So if we want to compute the distance between the nodes 1 and 3, so if we assume that our graph is unweighted edge, so we can just say the distance is 2 basically. But in terms of meaning, it has no meaning. But the goal of the graph or representation learning of the graph is to be able to embed each node into an Euclidean space. So on the right side here, we can see an Euclidean space projected in actually the reduced dimension of the Euclidean space, where we have kind of cluster. So we have a blue one, the red, and the green one as well. So it means that this network or this embedding is actually this is the correct embedding in the sense that we're trying to group a label together within the embedding space. This is the goal of the graph, and what makes this graph being called heterogeneous graph is because whenever we have a graph where we have more than two nodes, more than two labels. I mean, when I say no label is like we say classification. When we have more than two labels in terms of age and the nodes, it's called heterogeneous graph. Otherwise, we have homogeneous graph. So this is a basic definition of heterogeneous graph. And in terms of learning techniques, so we have actually in the state of the art, but I didn't cover all, but we have the famous one, this geometric deep learning. This geometric deep learning is, under this category, we have graph convolutional network, which is well known from the state of the art. And the graph convolutional network is a specific case of the graph attention network. And the graph attention network is also a specific case of the graph message passing. And on the other hand, we have a path-based learning. Path-based learning here means that we need, in order to learn the representation or the embedding of the node tree, we need to extract some meaningful path from the graph. So this is a path-based learning approach. And we have the well-known approach, this random walk approach, and then you may heard about this deep walk. And secondly, we have node-to-vec. Node-to-vec is actually a specific case of a random walk, but in the sense that the walk here are biased, but the random walk, the walks are not actually biased. And the third approach here is the metapath to vec. So metapath to vec is also a well-known technique. And the goal here is to it's actually a biased random walk as well, but in the sense that it covers some semantics. So you can extract some path from the graph, but from a particular semantic point of view. So this is actually what I can say about this heterogeneous graph, but I didn't cover all. Although today we can find another hybrid approach where we combine deep geometric deep learning and path-based approach. And secondly, let's now, okay, what about the table now? What is actually the table and what is the challenge with table? We have one table here, and with this table, I think I try to create three regions. So the first region here are row headers, and the second region here are column headers, and the the third region here, what I call the body of the table. So what is actually the meaning of this? How human, as a human, the way we want to read table is actually different from how we read sentence or how we understand sentence. For example, if we have an entry, this entry with hundreds, we can see that someone can read this entry as the weight of the component one. I mean, I'm referring to this large A, meaning component one. And we have another 100 here. We can also read it as the volume of component B. So it means that the entry or the way we give a meaning to entry rely less on the underlying text. It means that it doesn't matter what we have there, whether 100, 80 or whatever, it doesn't matter. But the meaning we attach to this entry within the context of this table is actually different from the number 100. So this is how human understand table. And we have been inspired by this, and then we try to, let's say, to formalize, to give a basic definition. And the definition here is actually what we are saying is that let's say we have a table entry. How can we characterize a table entry? So for each table entry, we call TA a text. So it means that it could be a set of characters, it could be a symbol or whatever. For example, we have 100 here, and BBA here means the bounding box, because whenever we have a table within a document, so the way we are processing it, it's actually different from the table coming from the database, because whenever we are getting data from the database, yeah, it's already structured, so we don't need to locate what are the bounding boxes. So BB here are referring to the bounding box, and what we call here like visual information. This is the visual information, and the text information is the TA. So we add another property which is really important. We call it semantic meaning. So the semantic meaning here is actually the meaning we attach to this entry within the context of the table. And this semantic meaning, we can also call it in this paper table semantic label. Table semantic label can be discrete. It means that, just like I described, we can have the weight of the component one. So this is a discrete way to define it. And it can also be a continuous space. In the continuous space, like you can get the embedding of the word 100. So this is a continuous way to define this, what we call table semantic label. In the state of the art, so people trying to use this continuous way. But in this work, we are introducing this approach with this discrete approach in order to learn to describe the table. And the goal of our table representation learning is actually to learn an in-context embedding vector for each semantic label. So this is actually the goal, what we want to achieve in this work. And how to achieve this? We start by giving a brief. We just cover representation learning techniques. I'm sure that you may know about it, but maybe we can highlight it because later on can be really relevant in this talk. The first approach here is the skip-gram model. So this has been used in word2vec, the famous word2vec for the first word representation learning on text. We also has been used in Node2vec and MetaPath. So the goal here is to be able, let's say we have a target word. The target here is WT. The target here is WT, and then the goal here is to be able to predict the context given a target. So this is the idea behind the skip-gram model. And this context it has a window size. So it could be, if you want to take your context to be 2, it means that whenever you have a target word, you have to consider 2 words before and 2 words after the target. So this will be your context. And later on, transformer, we have this famous architecture. This transformer architecture, I'm sorry, we have this max language modeling, so has been introduced in the transformer architecture used in BERT and Roberta. And the goal of the max language modeling is to be able to use all the input space at a time. So we do not have the window size as the skip-gram, but we are using the entire space. And the goal is to first of all, to mask a certain percentage of the input sequence and try to predict the mask sequence. So this is actually the goal. So this x/m, it means that this x is the input space, and then we remove the mask with the mask token, and then we're trying to predict. So this is the mask language modeling. We also have this causal language model. So causal language models has been used in all autoregressive models such as ChatGPT, but basically the goal here is to use all the left-word token to predict the next token. Just like the generative, whenever we are using ChatGPT, it always generates one token at a time because it's using the previous token to generate the next one. So this is the causal language modeling. So once I briefly recall what we call representation learning techniques in the state of the art. So we can then talk about this data modality. This is actually really important because it highlights our contribution. What we can see here is what is the difference between the semi-structured data and unstructured data. Because I believe that the way the semantic meaning, the way we understand table from the text are actually is actually different from the way we understand it from the table. So semi-structured data here, we are referring to table, could be table, tabular data, graphic or whatever. And unstructured data here, we are referring to the text, could be natural language. Remember that large language model has been trained on unstructured data, not the semi-structured data. And what are the key difference actually? So first of all, if we consider the unstructured text, the first column here, we have the unstructured text, which is a 1D, it's a one-dimension data, and it's actually sensitive to the permutation invariance. It means that if I give one sentence, I give one sentence, and then I swap, let's say, two words, it actually conveys different meaning. So unstructured text is actually sensitive to the permutation invariance, while the semi-structure is not sensitive. If I give you a table and then I swap column 1, column 2, yeah, the meaning will not change, the meaning of the entry will not change. So this is why we say it's insensitive. And it actually gives away, whenever we are talking about table representation, we should assess that our embedding or our method is actually invariant to the permutation invariance. It's permutation invariance. And the second column here, we are talking about a processing unit. The processing unit for unstructured text is a token. It could be a word or chunk of word or whatever, it depending on the tokenizer that we are using, but it's a token. While the processing unit for table or semi-structure is a cell or table entry. Now, the way we understand it, actually depends on the context. So any representation learning is actually linked to a context. So we have a context here. For unstructured data, we have the context here is we should look for a left word and right word token whenever we want to learn representation learning on the text. But for the table, we don't need to look whether the left or right. We do not even have the left and right because we don't know. The only thing we need to understand the table is a table primitive. Table primitive here means only the row column headers. The way in the previous table, I was trying to highlight how we can understand a specific cell. So we always link this with a corresponding column, row or column header. So this is a different, actually a different pattern that we find we can find in a structured text. And how we pass now, how to pass the unstructured text. We actually rely on rule-based approach. Rule-based approach, we always have this. You may know about it. Purpose of speech tagging. So it means that we assign a label, a grammatical label to each word. So we can say a word could be a verb, it could be a noun, could be a pronoun, could be whatever. And then you see the way we construct a sentence, because we always say if you put a noun before something, it means the next will be a verb or something like this, because the way we construct a sentence, you say the subject, the verb, and complement, right? So this is a grammatical way to understand semi-structured text, and this is basically a kind of rule-based approach. And for the table, it doesn't matter whether we have a noun, a pronoun, or whatever. It doesn't matter. What we want to be aware is the structure. And this awareness, how to pass this, we should leverage our visual and language modeling. The visual, it means that we know the position of this token, and then we're trying to link it with the corresponding headers and things like this. So this is what we are calling this talk and this paper, joint vision and language modeling. And the last column here is downstream tasks. For the text, we have a bunch of downstream tasks: name, entity recognition, question answering, text generation, and text translation. And for semi-structured text, we have visual question answering. Visual because the way we ask question is because we see some link. What is next? What is next? The volume. What is next? This entry. So this is a visual question answering. And information extraction, column type annotation, entity link. We have so many, and we actually think that it's important to introduce this task, what we call per cell semantic learning. This is actually what we are referring to our table representation. So we want to learn for each cell and in context embedding vector. Later on, we can also demonstrate this throughout this a really complex table. Even me as a human, at some point, you can be confused when you want to read to understand the table. So the first table here, we do not have the column headers. We only have the row headers. So how to read it? So we have one column here and the second column. How should we interpret the second column? So it actually depends. And with the second table, I mean table B, we have a table with a merge cell here and in the horizontal way, and then we have the merge cell here in the vertical way. This is really complex to understand. How should we read it automatically? Let's say you have a document and you have such a table embedded within your document. How should we pass it? It's really a challenging problem. And the next one here, we have nested headers. So we have the first headers here, and then we have another headers here within the same table. As a human, again, we can read it, because we are leveraging our human perception, our knowledge to easily understand the table. But as a computer, how should we do this? It's really complex. Now, how should we do this? Let's talk about this heterogeneous graph table modeling. Heterogeneous graph table modeling. So we want to be able to, we are mapping a table into a graph. So how to map? We have an initial table here, and then each table here has been indexed by the blue number. So the blue number is just the way to give a reference to each table entry. This is how we map it with the graph. So we have the corresponding heterogeneous graph table of this table, and each index here, for example, this node 22 is referring to this entire entry. And see the way we are preserving the structure, because we have a merge cell here. So this merge cell means that the entry of this value, it's actually hold for the first and the second column. That means the base and the accelerator column. And the way we're trying to preserve this structure at the graph level, if you look at the node 18, you will see that we have a two direction here. It's linked to the node 15 and node 27. And remember that within our graph, so we have the edges with the edge. We have the label for each edge. So the label here is, I think it's, I'm not sure if you can read it well, but we have left, right, up, and down. So if we are currently at node 18, we want to move up to node, or we want to go to the node 15, we'll move up. So this is the way, this direction. So we are still trying to preserve the structure of the table. So this is how we are mapping a table to a graph. I will not go through the detail with the algorithm, but I think we mentioned it in the paper. And later on, what is also important here is how should we label, because we are talking at this point. So this figure B is a homogeneous graph. We have a homogeneous graph here. So, but we are talking about a heterogeneous graph. So we need to label each node with a semantic meaning. And the semantic meaning here, for example, the node 2 is here. The semantic meaning of the node 2, it means that is the value of the base for the first component. So base actually is the first component, and we have another base here, which is a keyword. The same thing with the node 6. The node 6 is actually the color of the base. So it means it is this is the meaning we attach to this cell within the context of the table. So we label everything here. So this is actually the data that we that our training model will see. And during the inference, what are we doing during the inference? During the inference, we know all the table primitive. It means we know the headers, because if we don't know the table primitive, it means that we are even we as a human, we cannot give a meaning to this table. So we should always have a prior knowledge about it, and this prior knowledge is what we call table primitive, such as the table headers, the row header and column header. And the goal during the inference will be to infer the label of the body of the table. So this is the data we'll see during the inference. So we call it partially labeled heterogeneous graph table, and during the training we have a fully labeled heterogeneous graph table. And now we are already going deeper into this how we want to extract meaning from the table. We have one table here, and we have with the column headers and the row header. So the column header is CI, and the row header here is RJ. And how should we read it as a human? If I want to read, or if I want to understand the meaning of the entry TIJ, you agree with me that I should always link this with the CI and RI and RJ. So these are the row, the headers, what we call table primitive. So in our pipeline, we want to extract a reverse L path from the table. In order to understand the meaning of this entry TIJ, we need to extract a reverse L path from the graph. And this reverse L path, we can describe it here in equation 1. So we start with RJ, we move right. Remember again, this right is the H, so the H of our graph. We move right, and then we move right again. When we reach this TIJ, we move up. We move up to the CI. So it means that this target, for the target, this is the TIJ will be our target, and the ends node will be the header, the corresponding header of the target. So this is what we call semantic metapath. So we extract the semantic metapath from our graph, and then we will try to learn it the embedding from the SMP. SMP is a semantic metapath. And now we can briefly cover how to extract the semantic metapath. We actually implement this probability random walk because we are doing this automatically on graph. So we implement a semantic a probabilistic random walk. So basically, if you have this equation M here, and we can define a transition probability. So this probability random walk is actually a Markov random process of degree 2, because we are using the two previous steps to predict the next one. So if I'm, for example, at TIJ, I want to move to the next step. So I have to compute how many neighbors do I have in the up and right direction. So in the up and right direction, it will give me all the possible combination, and depending on the previous step, it means that up. If I'm coming from the up direction, I need to move up. If I'm coming from the right direction, I have two possibilities. I can either move right or up. So this is basically the transition probability we define here. What I'm trying to actually say, if I can, yeah. So if I'm, for example, at this step, so what could be the possible step? So I have two possibilities here. I can move from TIJ, I can move to the right position with the probability 1/5, or I can go up with the probability of 1/5. But if I'm already at just below the column headers, I need to go up. There is no way, because we always want to have the reserve L path from the graph. So this is basically this transition probability that we define in order to extract all the meaningful paths from our graph. And once we have the meaningful path from our graph, what can we do? We need to learn. So I'm already introducing our framework we call graph-based table representation learning. In this, we will first start with, I think, yeah. So let me first introduce our architecture, what I call here table representation in augmented transformer. So basically, whenever we have a table, so we can see a table here. Whenever we have a table, we need to extract the meaningful path. It means SMP from the table. And once we have this, we can use what I have a layer here, contextualize a cell embedding layer. And after this, we'll feed it into this multi-head attention. And we also have a semantic matrix here, so I will explain later what is the meaning of this semantic matrix. So basically, the goal of the semantic matrix is actually to make sure that each target in my semantic path will always attend to a corresponding headers. So this is actually the goal of this semantic matrix that we introduce here, and it's actually playing a role when it's actually acting as a attention mask in our multi-head attention. So this is actually the typical our table augmented transformer we introduced, and we are using only a 1 layer and 12 heads of attention. And in the state of the art, so whenever the state of the art, actually I'm referring to the architecture B just below here, state of the art LLM architecture. So whenever they have a table, they will flat it. So they will just flat each table in the raw way. So they will flat it in order to have what I call a pseudo natural language. And then they will extract the embedding. So I mentioned this continuous embedding at the beginning of this talk. And they will use the positional encoder. They will use the head they will use the caption, and then they will use different type of metadata. And they will use it and feed it into either transformer, Roberta, or whatever architecture. And then the learning here in the state of we found that the learning is actually in two phases. They will first do what we call pre-train, and later on they will do a fine tuning. So in our approach, we don't need to pre-train. Whenever we have the person semantic embedding, I think it's enough to for any downstream task. And a little bit of equation. So on the left part here is actually the same thing on the right with a figure, but let's give a little bit of let's say a representation or more equation so that we can easily understand it. So the pipeline of our architecture can be represented as we start with M, the SMP, meaning semantic metapath. We use the cell embedding layer, and then we have the embedding. We can use the encoder. We have after the encoder, we will have a Z, and then we need to decode Z here back into the original space M prime. And the decoder here is not a proper autoregressive model we know in ChatGPT, but it's just a fully connected layer just to project from the embedding space to into the original space. And the dimension here, so R, X and Z is actually in N times Q times K. N here is the length of the sequence, and K here is the embedding dimension. We can split X in terms of X1, X and X2, and Z as well. Why we can split this? So this first X, the X in the middle is actually referring to the target. And the X1 is the left part, and X2 is the right part. If you remember again, I mentioned it here. Sorry, yeah. So this is our target, and then we have the X1 here, and then the X2. The X1 here is the context right, and the X2 is the context up here. So we can split this, and then to steal now, because Z is the output of the encoder. So to steal the attention within the encoder such that the output Z cross attend to the correct meaningful embedding vector in X, we have this Z is equal to X1, A1 and X1 and W1. WV is actually the projection matrix for the value. To steal this attention, we are actually playing with our semantic matrix I introduced previously. I was talking about. So this semantic matrix here act here as a attention mask. Whenever we complete the attention coefficient, we use our semantic matrix to make sure that Z1, for example, will not attend to X2, because we think that it's not important in order to maybe to learn the embedding of the right part, we need the embedding of the left part. No, this is actually the goal of this semantic matrix, and this is how we our equation. And then here we are this WQ, WK, and V are the matrix, the projection matrix to project X into the Q, into the query Q and value space. I think this is common in the state of the art. So now, when we have this, I think we can already give this the pipeline of our graph table representation learning. So during the training, we have the input table here, and then we remember that for each entry, we need to assign a specific label or meaning. Once we have this, the second step, the step 1 annotation, and the step 2 during the training. I'm talking about the training is the first row. I have a feeling that you cannot see my mouse, so I don't know why, but the first row, the first step.
Really, yeah, we cannot see your mouse. Maybe if you are, I don't know if you're using PowerPoint, if you choose the pointer stuff, the
I'm
pointer.
not using PowerPoint. I actually uploaded my slides.
Oh, I see. Okay,
Yeah.
yeah, then you can just like let us know which part we should be paying attention to.
Yeah, I will try to make it. Yeah. So the training part here is the first row, and initially we have the table, and within the first row, we have the step 1 annotation. So we need to assign a label to each table entry. Later on, we construct what we call heterogeneous graph table, this HJT. This is step 2. And the step 3, we semantic metapath. We extract all the semantic metapath, and then we're trying to learn. And during the learning, we introduce what we call this. There's a specific learning here, actually. Here is the same thing as a max language modeling, but we're trying to max all different kind of possibilities. So it is an extension of max language modeling. And we feed it into our transformer, and then once when we have the model, during the inference, we have a table. Again, we only know the table primitive during the inference, and we want to be able to infer the body. And so I'm already talking about the second row of this figure. And later on, the step 2, we still construct our graph, and later after constructing the graph, we extract the path. And remember that during this, the extraction of the path, for example, we have at the step 3 prediction here, we have a question mark here. It means that we don't know this label, and we can use this the model we trained previously to predict the correct label, and then we'll have the fully labeled graph. So this is what the pipeline of our approach. And think now we can already talk about some experiment we conducted. So first of all, I would like to cover different data sets. So the first table here is we try to cover the overview of key differences between the table annotation data sets. And we can see that from a downstream tasks, most of the table annotated data sets have been designed for a table structure recognition, not a table representation learning. So we have one next here, Wikipedia table. So this Wikipedia table actually is something closely related to our table representation learning, but it lacks this semantic meaning. They have some specific label attached to each entry, but this label is actually a Wikipedia ID. So it's just a Wikipedia ID, but it's not actually a meaning. It's not actually a meaning. So this is actually the only data set we find. And then the second table here, we are just trying to give a basic statistic about our new table data set we introduced. So it's around 100 table, and we have the total, the minimum of the number of row per table. The minimum is 1, the maximum is 25, the average. And for column is 1 and 10, and the average is about 2.5. And the table structure, the table semantic label distribution now is the minimum is 3, and we have the maximum. The distribution is across the data set actually. and this is the average and the number of nodes. So the number of nodes, we have at least 4 nodes, and we have a graph with 59 nodes. So, and the average is around 20 nodes. And now, how are we going to compare this? So this is the pipeline. So we have the data set, we split it. This is a normal split, training and the test. And for the graph, graph to sequence to extract a meaningful path from the graph. So we are comparing with the baseline. The baseline here is a random walk and not to vec. And our approach here is a semantic meta path. And later on in the, we remove the duplicated sequence actually to reduce the bias toward the high frequency node. And for the learning method, we have the traditional max language modeling, and what we introduced, maximum inference max token recovery. So it's something I mentioned, this is just like an extension of the max language modeling. So we will have the training and the test, and then we will use different learning architecture. We'll use Roberta, the traditional transformer, and our transformer that we propose. And the result that we will report in this work is actually, we shuffle the data times time and report the average. So as the first result, we compute the micro F1 and the macro F1 performance during the training and during the test. So as the model, so we have the model learning architecture here, and the model architecture and the learning objective. So the model architecture here is, for example, we use a transformer combined with MLM max language modeling, and this parameter, this stack, it means that is the total number of parameter of the network. In this, we also consider two scenarios. The first one here is, what if we remove the edges from the sequences? So we consider sequences without the edges, and we also consider the sequence with edges. So without the edges, we report. Sorry. Without the edges, we have the report or the result on when using transformer and Roberta architecture. And the graph to sequence technique here is random walk and node to vec. So random walk is RW. Yeah, I'm sorry that my mouse, you cannot see my mouse because I'm pointing something really important here, but you cannot see it. But I'm talking about the without the first row and below without direction, H label. So we have the random walk, and then we have below the random walk, we have the node to vec. And this lambda here is the third column of the table. We have is a max, the masking ratio, because remember that during we need to max a certain percentage of the input space I'm trying to predict. So if we max, for example, 50% of the data, and then if we max 22%, so lambda here is a max masking percentage. And this is the total number of the fourth column is the total number of sequence, and next we report the metric during the training and metric during the testing. For when we consider now the scenario with edges, we can see that we can compare pre-learning architecture. It means we have the transformer combined with max language modeling, and below this we have transformer combined with our learning method, learning objective. And below this we have Roberta combined with max language modeling, and then below this we have Roberta combined with max with our learning objective. And the last row is our performance. It means our transformer when we combine with our learning architecture. In overall, we see that transformer, the traditional transformer, is the performance is a bit lower, and then Roberta is outperforming, especially when using our learning objective. It means the second row before the second row. And our architecture actually is competing with Roberta, but the training parameter here is far away less than what Roberta needs. So Roberta needs more than 2.5 million of parameter, while our architecture we only need 1.7 million of parameter. Yeah, I'm sorry that my mouse is not because I'm pointing a lot of things, but I'll try to be more precise. Yeah. And later on, we also conducted this evaluation. So we'll try now to play with the masking ratio. So what if we increase the masking ratio? So I'm referring to the first figure on the left. The masking ratio. So what if we mask from 20, 40, 80, and up to 100%? And then we try to compare this with different graph to sequence. So graph to sequence here, we have three methods. SMP, our method, random walk, and no-to-vec. We can see that the complexity of our method is actually less than the random walk and no-to-vec. But with our method, we are actually achieving a competitive performance compared to the state of the art. And let's move now to the next. This is the figure in the middle. We are comparing this with the transformer architecture. We can see that our SMP is still, yeah, we are performing better. We can see that we are performing better than the state of the art. And on the right figure, we compare this. We are comparing now different architecture. It means we compare our architecture, transformer, and Roberta. We can see already that our transformer, what we propose, and the traditional transformer, they have the same number of parameters. Roberta has more parameters than we do. And let's look at the performance. We can see that our method in blue is actually competing with Roberta, and the transformer in green is actually the lowest performance in this figure. So this is the next. So with the performance evaluation with respect to the masking ratio. And the next thing is we also play a little bit with the training percentage. So what if instead of taking 80% for the training and 20% for the test, we are only taking 10% for the training and 80% for the test, just to make sure that our model is not actually tuned to a specific data or how many information he needs in order to learn meaningful embedding. So even when we have when we need only 10%, it means this first column 10%, when t is equal to 10, it means we need 10% for the training and 90% for the test. We can see that our method is performing better compared to the others. This is our method is actually the last one here. We can see that we are performing better. At certain point, Roberta is taking it up, but again, so we can conclude that our method is still competing with is still competing with Roberta architecture. And now we can then assess the permutation invariance evaluation of our work. First of all, we have sorry. Well, I don't know what is happening here. Yeah, first of all, we have this the table, the figure A, and the figure B is a heterogeneous graph representation of the table. And the figure C is actually we swap the first row, the first column, and the second column. So we can see that you can see from the figure C, see the position of the node 2 and 0 compared to the position of node 2 and 0 on figure B. So we're trying to swap some row and column of the table, and the goal here is to be able to see how each model will perform in terms of permutation invariance. And just below here we have the result. So the first figure is a cosine similarity. So after getting the embedding from different architecture, it means Roberta, our transformer and the traditional transformer, we try to compute the cosine similarity within the embedding of each node. For example, we can get the embedding of the node 0 from the first heterogeneous graph, and then we get the embedding of the same node 0 from the second heterogeneous graph. You can see that they have the different position, and then we're trying to compute the cosine similarity. So this first figure, we can see that transformer is actually giving the highest, is actually more permutation invariant Roberta is more permutation invariant compared to our method, and the traditional transformer, is actually less permutation invariant. We can see that the cosine similarity drop across the figure. And just write this figure, it means figure B. We are talking about this table representation learning augmented transformer. So we're trying to inspect the attention coefficient given a specific path. So we actually trying to extract the attention within when we have path from the node 6 to 2. So from the node 6, we move to the node 23. From the node 23, we move to the node 27. From the node 27, we move to the node 30. 30. From 30, we move to 4. And from 4, we move to 2. The node 6 and 20, 6, 23, and 2 are actually the headers. So the target node here is 30, the node 30. We can see that the attention coefficient, look at the attention coefficient. So we have some part here, 0. And the node 30 is actually, the attention is more paid to the end node. It means to the corresponding headers. This is actually what we wanted to import to the training, to the learning mechanism, to be able to learn the correct meaning, meaning from the table. And we can see this from the embedding from the attention coefficient. And when we use Roberta is actually the figure C. We can see that the attention is actually uniform. So it's actually difficult to differentiate where to pay more attention in this using Roberta. And when using a transformer, you can still see, the attention is also uniform, which actually highlights that our table representation learning or our architecture is actually trying to learn a meaningful embedding compared to the others. And we can now give experiment on this public data set. So this public data set was actually designed for a downstream task called column type annotation. So the goal of the column type annotation here is to be able to assign a specific label to the entire column given a table. So this is actually the goal of the column type annotation. So we compare this with the state-of-the-art model. So we have actually several table representation learning model we have several table representation learning model on this data set. And we have the tablet, we have this tool, we have Dudio, we have Heterogeneous. This Heterogeneous is a recent one published in Norix, I think it was last year. And this is actually where we compare our performance. So when we compare with Heterogeneous, when we use the pre-training, so remember when introducing this talk, I mentioned that the current state of the art in table representation learning is done in 2 phases. So the first phase is the pre-train, and the second phase is downstream task. So when when we pre-train, and the total number of parameters is 179 million. So this is the performance, the F1 score, the precision, and the recall. And below this, we have the Heterogeneous without pre-training. So we can see that without pre-training Heterogeneous, the performance actually drops. And with our proposed method, because our proposed method, we do not need to pre-train. Actually, we don't need the downstream task because our learning phase is enough, the what we call per cell semantic learning. And our the parameter here is 65 million of parameter. So it's far less than what Heterogeneous requires in order to learn the embedding. And we got some competitive performance, especially when we compare this without training, we are performing better than Heterogeneous. So if we just consider the Heterogeneous without training, we are performing better. But when we consider with training, Heterogeneous is performing better. So but in our setup, we do not have this with pre-training setup. So this is the result on public data set. And we actually, we also trying to visualize the embedding. So what I call embedding visualization. Let's say we have this is a sample of a column-oriented table extracted from the test set. So it's actually made up of 3 columns. So the first column is home team, away team, and venue. Actually, 2 teams are playing somewhere else. And the goal here is to be able, in the data set, for example, this first column is actually, I cannot remember the label. So this first column, the label we assign to this column is a sport team. And the second column is a sport team as well, but the third column is a multi-label. It could be a venue, a sport facility, structure or location. So initially, when we got the embedding of this table, and then we're trying to plot it. We can see it on figure B, the figure below. On figure B, we have the initial embedding. Just look at how the distribution of the initial embedding of each entry. It's actually difficult to link each embedding to a corresponding column or headers. It's actually difficult because we have the headers here in color green, and then the cell are in red actually. And then after extracting the embedding, it means that when we feed the data or the embedding into our encoder and then we extract the embedding, we try to visualize the embedding. We can see already that there are kind of a clustering. The cluster, we can see we have the first cluster of the headers. We have the first cluster of the headers, and look another level of clustering. Look at all the square dots. You have the feeling that they are aligned in some way, in the horizontal way. So if you look at the square are aligned somewhere. It means that the columns embedding and the body of the embedding. So in the embedding space, so our architecture is trying to align everyone so that we can know that, oh, this is the embedding of this column. We can already see it from this embedding. And we look at the embedding of the circle. So we can see that the headers, the embedding of the headers and the embedding of the body, they are still aligned, so in the horizontal way. And third, we have the embedding of the cross, which is the cross is the second column. We can see that the embedding from the headers and the body, they are actually aligned. So this is actually demonstrate that our embedding is our architecture is trying to learn something really meaningful from the data. And then I think we can already conclude this paper by saying that we introduce table representation and method using heterogeneous graph tables. And this semantic meta path we introduce, which is the bias random walk to extract meaningful path from the graph. And then we use this NLP modeling on SMP to learn this visual semantic embedding. Visual because we are leveraging the visual information from the table combined with language modeling. And we also introduce our our transformer architecture, which is the position-free encoder, and our result is somehow competitive to the state of the art. And then, as a limitation, I think the complexity of this is really complex in the sense that generating, for example, the SMP when the number of row and column of the table is large. Yeah, it's not a polynomial problem. So this is one limitation. So I will end my slide here, and then yeah, I will be happy to provide answer to any question. Thank you.
Awesome. Thanks for the really enlightening presentation. Really, it was pretty cool. Also, pretty cool that we could have got like competitive results against work that was published last year in Europe. I mean, you're actually outperforming them in some instances. So let's see. Okay, so I guess we can now take questions. So I don't know what is the good strategy to use here. I guess I will just go through the chat and then kind of take from top to down, just like read up the questions for you.
Yeah, I don't know how to read it.
Let's see.
Maybe that's the full screen. You can see this. I cannot see it.
So the first question was actually from Saskia, and he kind of like came a bit late to the presentation, and he was basically wondering like, what is the purpose of graph table modeling? Like, why do we want that?
Yes, actually, it's actually a very good question. Yeah. The purpose of this graph table modeling is that the initial table itself, it doesn't provide a way for us, for example, to let's say to implement a random walk from the initial table, and that is why we try to map table into a graph, so that because we know with a graph we have a lot of tools, we have a lot of facility, we have a lot of available tools online to implement it. For example, we have to implement this random walk, so we're using I think there's a Python tool, how to call it, network X. So we have a lot of facility. So that is why we are using this graph modeling thing. And that's, yeah, it's actually, we also have another, I can also answer this, support my answer by saying that whenever we have a graph, so we can, today we are talking about this interactive chat. So how can we interact, asking questions and get the answer? With the knowledge graph and techniques that exist today, whenever you have a graph and the embedding, you can already get the answer by asking natural language from the graph. So this, actually the goal was to move from the non-modeling structure, which is the table, to a modeling structure. I hope it's clear.
Yeah, I think that makes sense. And so like I guess one point here was that, because like how there have been demonstrations, for example, where you can take something like ChatGPT and then you just like flatten like whatever is your input. So for the table in this case, you just like flatten that to be like a sequence, just pass it to ChatGPT as input, as prompt, and then you ask your question in there, and then it's just going to like give you output. And at least for the demonstrations that they show with this model, it seems like it's actually understanding what is in the tables. But I guess like this more precise or specific way of modeling or embedding the tables is better than
Yeah,
approaches like that.
yeah. Actually, when you flat a table entry, you will not have what we call natural language processing, natural language, but you will have what I call pseudo language. Let's say you have a table, something like, I think I can quickly show this here. Um, yeah. Sorry. I'm moving up again, up, 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 up. I think it was, let me go up. Whoa. It's actually, I think next time sorry, I think I have an example of the table. Yeah. Oh, there's a lot. Whoa. Sorry. Yes, this is, for example, an example, this table. So if you want to flat this table, you've allowed 2011/A, and then you will have 100, you will have 100 later on, and then you will have this /B, you will have 80, you will have 100. So it has no meaning. So this is a pseudo language. And remember that large language, although there are some people have tried it, and then you will have the feeling that it gives you something, because they are leveraging the power of the large language model in order to understand this. But from this pseudo language perspective, it's actually very difficult to extract the specific meaning of the entry in this context. They will still learn it from the entire meaning of the word 100. But the meaning of the word 100 or in this context, yeah, is still missing. And that is why with this modeling, we are trying to bring the structure awareness in the context of table representation learning.
So then, like in that case, is it fair for me to say that the biggest advantage of this method, also kind of given the results we were showing later on, the biggest advantage is to have is that it's kind of like data efficient in some sense. Like we're showing how, for example, also parameter efficient. Like we're showing how you're getting competitive results with like much less parameters than.
Yeah. Actually, we are arguing that we do not need a lot of information, because this actually what we foresee to conduct in in the near future is this few shot learning. Even when I give you a specific table, even with one table, you can only grab the meaning. You don't need the entire sample of the same table to grab this meaning, right? So this few shot learning, the way we are learning with actually very less parameter, it's actually a sign or symptom to say that it's aligned with this few shot learning as a human behavior when you want to read a table. So what you are saying is actually is totally correct.
Yeah, that makes a lot of sense.
Yeah.
Cool. Then moving on to the second question. So Futse asks, I am curious about how updates are managed with this approach. Specifically, are new embeddings generated when the data changes? And how are these new embeddings integrated with the previous embedding?
Yes, actually, the new embeddings are, we always generate new embedding. It's actually this actually depend on the downstream task because I think I mentioned yeah, this is actually the yeah, we have two way of the previous, I guess the specifically new embedding generated. I suppose that we have the initial embedding, and the initial embedding in the state of the art will refer to the embedding of the text itself. This is the initial embedding, and finally, when you flat the table entry, you agree with me that you will end up with another representation. This will be the new embedding. So whether you are using a large language model, you will still get, you have the initial embedding and then you have the last embedding. And in our approach, you will get the embedding directly linked to the corresponding headers. So in the large language model, you will get an embedding, and then this will be the pre-trained phase, and you will need a downstream task now. So the downstream task is actually you get the embedding maybe for classification problem or whatever.
Yeah.
So yeah,
So then kind of tying to that, because I see she kind of followed that up to saying that she's interested in understanding. So the reason why she's asking that is because she's interested in understanding both the process for updating your embeddings and also how the system handles the transition between the old embeddings that you have learned versus like the new embeddings for your new data set.
yes, it's actually a very good question. How the system handle this? I will go back to my slide. Yeah, thing is supposed to be somewhere here. I think it's before this. Before this again. Oh. Yes, this is the figure actually. So the initial embedding she is referring to is the X. So this is the initial embedding. So after the encoder, after going through the encoder, I will have the Z, which is the final embedding. So how this works is, yeah, this is the traditional transformer, and I didn't want to go deeper into this because, yeah, I think it's the main difference I wanted to highlight here is how our semantic matrix will play, how this semantic matrix is playing, what is the role that the semantic matrix is playing within the attention coefficient. So whenever I have this X is the initial and Z is the output, or this is the encoder. And let us have a look at the right figure, the right upper figure, our architecture. So whenever I have this X, so X will be the output. We can see it from the output of the contextualized cell embedding. So this will be the output. And then I have to split it into the query, the key and value. And then this X will also go through this semantic matrix. And we have the attention coefficient, the military head attention. So this will be the normal process. We know about the military head attention. But inside this military head attention, how this M is influence the attention coefficient. So it's actually below the equation A is equal to softmax, where we project the query and the Q, and then we use the max M. This is a specific max. So this is the process how we are transforming the initial embedding to a final embedding. I hope it's clear.
Okay, so I think that makes sense. So what you explain right now is how you kind of transform the initial
Yeah,
embedding or representation of
yeah,
your input, how you transform that into a more useful embedding that takes into account like
yeah,
the headers and
yeah,
the row headings and all of that. Um, I guess also maybe part of her question too was, and I'm just assuming here, maybe part of her question too when she mentioned that data when data changes, it's like you have trained this on a particular set of training sets, right? And now you have the embeddings for that. Now
yeah,
you are presented with like a new data, like for example, like one of those downstream tasks that you mentioned there.
yeah.
Do you use the exact same embeddings? Do you fine tune the embeddings? If the embeddings are going to change, like how do you change that?
Yeah, this is actually a very good question. So, this is, yeah, even in traditional machine learning, um, if we train, for example, a model to classify, let's say maybe a dog, and then later on we want to detect something else, or shoes or whatever we need, even though we propose a methodology for classification, cat or dog, something like this. If we want to detect shoes or whatever, so we need to train on this data. So it's actually the same thing here. But what makes people, yeah, this question always, I have been asked this question for long, because uh, whenever we have data a table, we have a feeling that the table are the same. We always have a feeling that the table are the same, but they convey different meaning. If you get table from medical document, it has no link with table from data sheet, let's say from adhesive material, or data sheet from fridge or whatever. You will see that even the key parameter will change. So the meaning it conveys actually totally different meaning. So even in this case, just to answer, so when the data change, so we need to actually apply the same methodology. But as long as you are using the data or the table within the same context, you don't need to retrain it.
I think that makes a lot of sense.
Yeah.
And I guess also if you are using if you are using the table in let's say it is a different data set, but um, it is in some sense belonging to the same type of setting as like when you train it. Like
Context.
let's say for example, yeah, the same context, or like
Yeah,
maybe it
you
is
don't need to
knows
retrain it.
about like
Yeah,
um,
you don't need to retrain. If you train it on medical documents, so whenever you see table with medical document, they may have a common term, they may have a common context, so you don't need to retrain. But it's actually the same thing, but it's just that in this context, table, we as a human, we always see table as the same thing, but the context actually differ in this.
mm, okay, I think that makes sense. So like she just added that so the change will be included at the next trading phase then.
The change will be included at the next training phase then. Um, I, I
So
think that I'm not getting the context of the change. The change of
So I think so before what she was talking about the data changing. So I guess what she's and the embedding changing because of that. So I guess she's just trying to confirm if the change in your embeddings will happen at the next training phase when the data set changes. I think that is what she means.
yeah, actually, if the data set, if we change the data set, it means that we apply the same methodology. So yeah, after the training, we will still get the embedding. So I'm not sure that is I'm providing the answer to this.
Good. I think she's happy with that. Um, cool. So basically, you kind of always applying the same process that you are showing on this in this slide to any new
Yeah,
data set.
yeah, in the new data set, and it doesn't matter. Just like I said, a table always we have a feeling that table are the same. Of course, they are the same in the strength of structure, but in
Mm,
terms of meaning, it's actually different.
cool. Cool. That makes a
Yeah,
lot of sense.
yeah.
So Jonas, in that in a way, okay, I think I butchered his name. So Jonas asks, thanks, or so he says thanks for the presentation. What motivated you to use the random walk, and what is its effect on the method?
Random walk. Yeah, well, so Actually, I use random walk, but in the way that it's actually a biased random walk. It's not a traditional random walk, just like we say we are walking randomly on the graph. So, but it's a bias, and the motivation that the main motivation was that I wanted to extract the meaningful path, the path from the graph. And this path should be meaningful in the sense that it should always align with the way human reads or understand table. And this way human reads and understand table is actually whenever I give you a table, you will always trying to form a reverse L. So you're always trying to find what is the row column headers and what is the row header and what is the column header. So this pattern actually is a L pattern. And how to extract this with a biased random walk is not actually a normal random walk, but it's a biased random walk. Bias in the sense that we are trying to introduce bias in the transition probability. So it's not we do not extract any path from the graph. No, it's actually meaningful path using. I hope my answer to this question is correct. Although maybe I think he was referring to this bias random walk because we later on compare our bias random walk with the traditional random walk.
And so let's say, assuming that what he was talking about was the bias random walk, so then what was your motivation for making it biased down using like a traditional random walk that you use in
Yeah, like I said, the main motivation was actually we wanted to mimic the way human read table. This is the main motivation. We wanted to mimic the way human read table.
Did you try just now? This is kind of like out of curiosity from me. Did you
Yeah.
try making it? I think you probably show it, but probably miss it from your results. Making the like having the all of the other parts of your approach remain the same, but making the work uh, one on bias or two bias towards different other
Yeah,
distributions.
yes, actually, I talk about three. We compare this with the no to vec. No to vec is actually a bias random walk already, but it's implemented bias random walk using a Markov random process of degree one. So we are
What does that
introducing.
mean?
Sorry.
What does that mean? It is
So in
using like
degree one, it means that in order to infer the next position, I need the previous position. I mean only one previous position. And what we are talking about, our method is we need two previous position.
I see.
So we compare this with a normal a random walk, a biased random walk of degree one, which is a not of it, and then we use our semantic meta path, which is also a biased random walk of degree two.
Okay.
Yeah, I
And
think you probably missed because of this mouse. You couldn't see my mouse. Yeah, you can see it from here. So no to vec. This N to V is no to vec. It's a bias random walk and the traditional random walk and our method SNP.
okay, good.
Yeah.
That makes sense. Makes sense. So it means that this bias random walk for tables is at least demonstrably the better way
Yeah.
to do this. Awesome. Then the next question, this comes from Saskia Luding. This kind of additional representation might prove interesting for large language model reasoning too. Is that correct?
Yes, it's actually correct. I really like it. I really like it because just like I mentioned, whenever in our embedding, if you have a meaningful representation of each node at the graph level, in the large language model reasoning, actually you can directly interact with. Let's say you can ask question, what is this of this? You will see that you will embed the query next to the correct embedding of the answer.
Mm,
So this is a direct reasoning on with large language model. So it's a really I really like it.
that's interesting.
Yeah.
I guess also, so like the test you did, the Dalton test you did didn't really kind of have like such reasoning tasks, like high degree of reasoning tasks. Do you kind of like envisioning kind of testing that and actually seeing how helpful it is for
Let's say,
using that.
what do you mean by reasoning tasks like Q&A?
Yeah, so like a Q&A that kind of requires maybe kind of like I don't know, like performing various operations on like the table columns and then using those results to like do
Yeah,
more operations and then figure out
yeah,
the correct way of like the correct plan, right,
yeah.
of operations to do.
Yes, this is actually we want to investigate this actually, but although we are not too sure, yeah, we are not too sure about the results. So because yeah, now it's a large language model, so everyone is talking about the Q&A. And in terms of table, large language model itself, it can generate a lot of things. So you will see that it has done a lot of downstream tasks when you are talking about table. Downstream tasks, for example, the column type annotation. I don't know in which case we can use such a reasoning, because with large language model you can generate such a meaning, right? So so we are still hesitating within what is the next direction, because we see a lot of perspective in this area of table representation learning, but we need to be to pay more attention on what to focus, because otherwise we may lose a lot of time on, not, I would not say useless thing, but not really relevant for the humanity, because at certain point we want to, everyone want to see his model out and running as a plugin somewhere. So yeah.
Good. Okay, I think that makes sense.
Yeah.
Awesome. Then I think the last question actually comes from Naomi Wamba. So she asks, please, I didn't see clearly the labels assigned to each node and slash or edges when constructing the THG.
Yeah, heterogeneous graph table. This mainly, I think she is referring to this.
Yeah, like because like the also because of the size and maybe also like the
Yeah,
fact that couldn't of like put your mouse on the correct
yeah,
stuff.
the mouse. Yeah. I thought I was doing it correctly, but I noticed later on that you may not be seeing what I'm pointing. This is actually how we assign a label. Yeah, please, I didn't see clearly the label assigned to each node. So the label we assign to, for example, the edges. I will start with the edges. So we are using a simple direction, like the node 15 is on the left of the node 17. So we're trying to connect it with the node with the label left. And since we have to maintain the consistency, if you are on my left, it means that I'm on your right. And if I'm above you, it means that, so we're trying to use this for connectivity label to label the edges. And then for the nodes now, we know the primitive of, like I mentioned, the table primitive here are column and row header. If we don't know this, we are not talking about table. So in this case, in this table, for example, the table primitive here, we refer to the first column as, we call them keywords, because this table was extracted from adhesive document, and then they were calling each here, for example, they were calling by volume, by weight keyword, right? So I call this entire keyword, and then the base, it means node 0. It was called the label of component 1 in the domain knowledge. It doesn't matter. We can read it base, but the expert in the field, they read it differently. So the meaning they give to this is a label of component 1, and we have the accelerator, which is the label of component 2. So what is the color, for example, of the label of component 1? The color here is the keyword is white, and what is the color of component 2 is white as well. So with this, we were able to label the entire row headers and column headers. And then for the body now, we're just trying to make it as a tuple. The node 2, for example, we call this label of component 1 to just make up our graph really simple. And the node 6 is also a label of component 1. The node 6 is also a label of component 1. It doesn't matter. But we try to make it just simple for us to understand the concept. This is during the training, and then During the inference, we do not know the body. We do not know the label of the body, and we will try to infer what is the label of the body. I hope it's clear now for Naomi.
I think that makes sense.
Yeah, I'm sorry that
So
you
like
cannot see my
during
map. Yeah, go ahead, please.
so I mean like during inference, you will kind of convert
The
you kind of convert your table to this like HGT,
the
but you
SMP,
won't.
yeah, SMP,
Uh, uh, what is
the
that called in
semantic
SMP
metapath.
again?
Yeah, the
Okay,
semantic
okay.
metapath. Yeah.
So you do that conversion, but then you won't assign this node labels to it. You will let
Yeah,
the
I will
net.
not assign because if I convert from let's have a look at the last this last figure during the inference. Let's have a look at the we will get the path 4, 2, and 0, right? We will get the path 4, 2, and 0. But the thing
Which
is
one are
that
we looking at?
sorry,
Which one are we looking at? Which node are we looking at?
I'm talking about the last the right figure
The
below.
bottom right.
Yeah, the bottom one. Yeah.
Okay.
So we will have a path like 4, 2,
Mm,
and 0. This is a semantic meta path, right?
mm,
And then we will try to infer what is the label of what is the label of the representation of the node 2. Yeah, and then during the inference, this will be masked because
mm.
so this will be masked, and the train model will try to predict it.
I see. Okay.
Yeah.
Okay. So then that kind of like maybe ties into the last question that or the follow-up question that Wamba asked. So she's saying, so are you learning a multi-label classification model?
Um, This at this point, it was not a multi-label classification problem, but later on, during when we were working on a public data set, because the data set was a multi-label classification, so we adapted a little bit our training loss. Instead of using this cross entropy loss, we are using the binary cross entropy loss to take into account the multi-label classification. So our methodology, we can adapt it to any kind of other multi-label, multi-class, but this is already a multi-class, but for multi-label, multi-class, we also apply it on public data sets.
So let me just repeat that to see if I understand. So during training, you will kind of like or like when kind of like inferring. So during training, the way you label a data set is like you use this kind of like this approach you just mentioned for the
Yeah.
bottom left figure
Yeah.
to kind of like label each node.
Yeah.
And but then when you're down doing inference, you will let's say for example you're inferring um, what is the label for this node 2
Yeah.
given the context of node 4 and the context of node
Zero.
0 you
Yeah.
will max out the label for node 2 and then
Yeah.
the model will have to like output what is the correct label
Exactly.
for that.
Exactly.
And then that is like doing like that's your process for embedding learning and embedding inference for each
Yeah.
node.
Yeah.
Now, when you're kind of doing downstream tasks, depending on whatever downstream task it is, if it's like a classification task, for
Yeah.
example, then you kind of use your binary cost entropy loss for that task, but you won't. And I think you keep the network parameters that outputs the embeddings will keep those frozen. Is that correct? You will only be
Uh,
updating.
Forcing, you mean during the inference?
Yes, and
Sorry.
so I'm doing training for downstream tasks. Do you freeze the
I, yes, actually,
parameters for the embeddings?
this is actually a good question. So, just like I mentioned again in our training methodology, we don't actually need the the downstream. I mean, we don't need this what we call downstream tasks, and then once we train, we have everything we need actually. For example, for this column type annotation task, the goal of the column type annotation task is, for example, with this table, if we take the figure A, the goal is to give a specific label to the entire column, to the column headers, basically, right? So these column headers, you will assign a label to this. This is the goal of the column type annotation. And then you will take the second column accelerator, you will give a specific label. So in this context, how we try to adapt it in our model is that, so I'm talking now about the bottom right figure. So if I want to apply the column type annotation here, I will only mask. So all the rest will remain the same, but I will mask the headers. Assume that I don't know the headers. So the way I predict it, I'm already doing the column type annotation. So which is actually different from what in the state of the art. They will try to learn the embedding all without any label, and then later on they will have a fully connected layer for classification.
Oh, I see. I see.
So in this, I don't need it. So that's why I'm emphasizing that what we are doing is when you have the meaningful embedding is all you need for any downstream task. And this is a similar question. If you are talking about question answering, let's say I have a table like this. I ask you a question. What is the base of the what is the color of the base? I'm talking about the figure A. What is the color? Color is the node, right? And of the base. Base is the root header, right? You can see that the way that I have color and base in one sentence, so the embedding will be closer to the node 6. So I can already extract the answer here.
I see. So
this
like
is
that node 6 will be we have like you will mask that, and then the model will have to like infer
exactly. So yeah, we need all, and because I didn't know, we actually have this. We opened up this app to Bpost. Is a Bpost here in Belgium. Is a company for this mailing packaging or whatever. So they are already using this tool, but it's an internal process. And if someone is really interested, I can create a password just for a few hours if someone wants to test it directly. But yeah,
that's really cool.
Yeah.
Awesome. So I think like if you don't mind of putting that in the KmerAI WhatsApp group, I think that is really cool. Like
yeah. But that will be for a few hours because I will I have to they should give me a power to share this output. Yeah.
You don't want to abuse the power. That makes sense.
Yeah.
Cool, awesome. Then actually related to
there's a question here. Is there some public available GitHub notebook emphasizing your algorithm or a Hugging Face repository leveraging on your work? Yes, this is actually really good. I have a repository on GitHub where you can find all the data sets we use, and the notebook not yet, and also for the Hugging Face not yet. Actually, I'm not allowed to share this at the moment because we have a patent for this algorithm, and then it's still under evaluation at the European office. So I opened it up. I think it was a month ago, and then they told me not to rush because of some internal evaluation and things like this. But you can already find all the data set and the methodology and everything on our GitHub. So maybe I can share this GitHub here in the chat. Maybe give me a minute. I will share this. But the notebook is not yet available. Yeah, it will require some time to.
Nice. Are you putting the link on the chat here?
Yeah.
Yes. Let's see. Cool. So as you are putting that link, there's one last follow-up question from Naomi.
Yeah. This is a mass learning framework. I feel like to do so, one needs a lot of data to learn the context. Or am I wrong? You are not wrong. Basically, you will need a lot of data if, let's say, you want to learn a new language. If you want to learn a new language, you will need a lot of data. But in the context of the table, you don't need a lot of data because you always use the table primitive. The table primitive is what you know about the table. So you are already using your pre-knowledge. Let's say you have a table H. You will not learn the embedding of H. You know already the meaning of H, right? So, but how to combine the H with something to convey a different meaning. So it's actually, I think you don't need a lot.
So, so if my understanding there is correct, the kind of idea here is if you're doing kind of like general natural language processing, then you actually don't make any assumption about the language, and so you basically have to learn everything from scratch. Meanwhile, in this case, because you actually know that you are dealing with tables specifically, it's actually like a lot of knowledge about tables that you can already encode in your learning process to
You are not
tables
actually.
application.
It's actually we don't need something from scratch, and the only thing we need is table primitive. If we don't have the table root and column headers, even you, let's say I give you a table without headers, how will you read it? So it has no meaning. So we need actually table headers, and the table headers is already a language. It's our prior knowledge, so we don't need to learn again what is the representation, what is the embedding of the age. We don't need it. It's known. That LLM or ChatGPT will give you a very powerful or meaningful embedding for this. But now, how to combine it? Actually, the goal here is to be able to mimic how human read table, because this pattern is still missing in all natural language processing techniques, like even in LLM. Because in this talk, I was trying to demonstrate the key difference between the natural language, which is one dimension D, and the table. We see this permutation invariant things. So if you permit the language, so you are actually you mess up the meaning of the embedding. But in the table, it doesn't matter. Permit whatever you want. The embedding should remain the same.
Actually, as you are mentioning that, does that mean that you don't use positional encodings?
Yeah, I don't need positional encoding in my framework. It's a positional free encoding. Yeah.
That's very interesting.
But we were also a little bit scared, not scared, but shocked when we use, because transformer is a positional encoding. We see that when we use positional encoding in the context of the table, we observe a drop of performance. But when you use, instead of sinusoidal embedding, if you use the embedding position, because BERT actually learn the position, you actually, we are competing with the same embed. So it's slightly permutation invariant with Roberta. But when we use sinusoidal embedding, because sinusoidal embedding, the embedding is known of the position is fixed throughout the sequence.
I see.
Yeah.
That makes sense.
Where should I post this link now?
So I think you can put it on the chat here, and later on, if you don't mind, you can also put it in the KmerAI group. WhatsApp group.
I just post it. Can you see it?
Yes, I see it. Let me just put it, just copy that and put it in the public chat.
Yeah.
Awesome. Let me just quickly add it to the KmerAI group. Awesome. Cool. I think that's pretty much it for all of the questions. So thanks a lot, really, for the really enlightening presentation, and it was really insightful.
Yeah, thank you, and I hope it met your expectation, and yeah, it was really nice. Yeah, to give a talk here.
Awesome. Thanks. Also, thanks to all of you guys for attending this presentation. It was really nice having all of the interaction and all of the questions. I think it was really nice questions. Awesome. In that case, I don't know. I'm not sure if I'm missing anything, but I think that is pretty much it. We can call it a day. Awesome. Cool. Cheers, guys.
Cheers.
See you all next week. Bye-bye.
How to edit?